I'm going to be talking about math and big systems. I have to warn you, though, there may be, like, if you've had a bad math experience, there will be a lot of triggers here. I'm really going to paint a very bleak picture. So if anybody has taken, like, a stats class or stats for engineers or anything like that, you may leave slightly depressed. So, okay. I got that out of the way. If you don't recognize me, I have a lot of varieties of hairstyles and beards. Those are all actually me. I'm the CEO of Circonus. CEO stands for something about regret. So when you build a monitoring company as a SaaS product, you simply have to be more available than all of your clients combined ever. And when you're not, you memorialize that in every graph you show someone forever. So it's actually a really challenge. Our CTO always asks me, you know, like, why in the fuck did you run a monitoring company? That doesn't make any sense. So what are we going to be talking about today? So we're going to be talking about basically taking data in, right? So we're taking data in off of devices. Everything from octets off of switch ports to, you know, power draw through a PDU to maybe CPU idle, CPU counters on a box, maybe syscall latencies, disk latencies. And then we might take that up the stack a bit. I'll probably keep it super technical, super systems oriented here because I think it'll relate to people more, and probably turn my sound off. But we also take other data in. So we have customers that are putting things like Twitter sentiment, like the number of tweets that are happy about their brand versus sad about their brand. Turns out that's a number too, and you can put that in a system, and you can start to correlate that with things like database latency and all the other ops screw-ups that you have. So, so the real question is we have a whole bunch of problems when this data comes in because data is so varied in type. So just quickly enumerating the problems, we need to understand what the signal looks like. So we have the signal of data coming in, and I'll show in a second how those things look really different. And then we have to manage two different types of modeling in the system. So if I have data coming in and I want to know where I'll be in 6 months, I should probably look at a trend that's more than 5 seconds old. I should maybe look at the last several months of data. That's really an offline problem, right? I have an offline data set. I need to build some sort of model around it. I need to do some regression analysis or forecasting or something like that. That's a very offline problem. And then I have data flowing in at millions of metrics per second or billions of metrics per second. And I need to be able to say, hey, that box is broken. Right? And that is not something where you, a billion times a second, are going to go check an offline model, right? So that's a very online problem. So I'm going to talk about a little bit about the online approach and the offline approach and how those two approaches are incredibly different and how them being different actually screws you badly. And then how do we reconcile those two problems so users don't hate us? And then I'm going to talk about all of these problems in an actual large system context, and that's where sort of despair and depression come in. So what's the approach, right? So what is the approach to this problem, right? There's a lot of different things. If you go to any sort of monitoring and metrics talk where they're trying to figure out anomaly detection and things like that, you get all these off-the-wall models, statistical models, machine learning models, supervised or unsupervised models. You have people that just like make up shit. And it turns to work somewhat well. Ad hoc models really work quite well sometimes. But the truth of this problem is that this is a really hard math problem with a lot of data. And I took, I guess, 8 years of college-level math in the various pursuits that I had in my little hole in academia. So my language and my understanding of math are quite good. But still, I just hired PhD mathematicians to solve this problem because that's what they do for a living and they're really smart. So what we did was we took our models, we took our data, and we took our customer use cases of like, you know, basically we have all this data and a customer said, hey, my shit broke last Thursday at 3 p.m. and you didn't tell me about it. I really would have appreciated if you told me about it. So then we look at the signal, we look at 3 p.m., we give it to a mathematician and we say, how do you get this signal out of that noise? And they apply a PhD, and you rinse, wash, and repeat. And we just keep doing that. So the first problem, though, really isn't how to detect the anomaly. It's how do you classify the signal that's coming in. And this is a really easy thing to demonstrate. So if anybody's ever done switch ports, who monitors network versus system versus what? Network, system, apps. Okay, systems, app. Okay, good. All right. So this applies to API requests per second, which are very app thing, maybe bytes per second or packets per second out of a switch port, or even like CPU idle that you're trying to measure. All right, so there is one rule when you measure things. This has nothing to do with math. This has to do with accuracy, is that you should never be measuring the rate of something. Right? You should not be measuring the percentage idle. You should not be measuring the packets per second. Because if you miss a window when you measure, you have no idea what happened during that window that you missed. So instead, you should be counting volume, right? Because we have this really awesome thing in math called rise over run, where we can figure the slope of a curve, and we can figure out the rate. So what you should be doing, instead of measuring packets per second out of a switch port, is you measure the total number of packets sent. And then sometime in the future, you ask it, how many did you send now? Right? Now you have two values, subtract the two of them, you divide by the difference in time, and now you have a very accurate packets per second over the time interval that you measured. So an API request graph might look something like this, but the data behind it doesn't at all look like that. It looks like this. Right? The data behind it, this is like, I'm doing a lot of API requests. I've done more. I've done 1 million. I've done 1.2 million, right? And then you reset your API service, and it's like, hey, I did 12. I did 400. And it resets. So you have a signal that looks something like this. And detecting an anomaly, like a human being, unless you're depraved or spend way too much time doing what I do not see this when you see this. Right? Like mentally deriving that is not something that human beings are very good at. Nevertheless, this is the signal that's coming into the system, and you actually have to have methods where your analysis systems need to be able to classify this as a signal that I need to do, in this case, a forced positive derivative, so discrete derivative. So what we're doing here is we don't actually care about this signal. We care about the changes in this signal over time, but only when those changes are positive, because we don't want to catch the resets. Those aren't actual real. Those are manifestations. Those are implementation problems. So if we take the difference in value over the difference in time for all differences in value that are positive, we get a beautiful graph like this. Great. The question is when this data is flowing in at 1 sample a minute or 10,000 samples a second, how do you dynamically classify those signals so that you can apply your algorithms to this signal as opposed to this signal, right? So to complicate things even worse, little insight into categorization problems. What happens when you have a signal like the amount of disk space used on a drive, right? So how many people here monitor disk drives and say, if it's too full, page me? And this is a great question. You set it to something like 85% or 90%. Am I in the right range? Okay. And when you get paged at 3 a.m., that page, your remediation effort is to change it from 85 to 85.1, right? Right? Something like that, something close, because the reaction that you can take at 3 a.m. to that problem actually isn't a rational reaction, right? I mean, you already hit the problem. Maybe what you should do is order a new drive or schedule a task for an engineer to expand a volume or something like that. So the problem is that the total space used of 85% is a really useful thing to track. That's a great capacity planning metric. I don't want to derive that. However, if I want to look at my growth rate over time, I actually do want to derive that. So looking at the change of disk space used over time, I can see exactly how quickly I'm filling my drive as opposed to how full my drive is. And both of those things are incredibly useful. So now I can't categorize that signal into one or the other. I can categorize it into both. So you do have this like brain melting exercise when you actually have. So the way that we do this is that we have human beings look at these signals and say, this makes sense to look at this signal this way. And we have millions and millions and millions of streams of data coming in. And we'll have our users, they're very strong hints in our system. When someone drags a disk space metric into a graph and they show it as a gauge, pretty good hint that they actually wanted to look at it as a gauge. If they derive it as a counter or do a straight derivative or a second derivative or an integral of that, when they do that, there's a really strong indication to us as the operators of the system that that visualization, that treatment of that data makes sense. So then one user's vote doesn't count for anything. It's just like airline miles. When you have a lot of them, it starts to count a lot, right? So then what we do is we look at certain types of data like disk usage, and we see a large group of people looking at it as a gauge and looking at it as a strict derivative. And then we say, okay, well, disk usage type metrics are these types of things. So then we take a signal like that and we start extracting characteristics from it. We extract, is this monotonically increasing? Is it smoothly up and down? So disk usage would be smoothly up and down as I delete some data. It doesn't ever really reset to 0 unless I wipe my drive. So it has a very different sort of pattern than, say, API requests, total API requests, where when you reset your load balancer or whatever's accounting for that, it'll actually drop to 0. So we're trying to extract these characteristics from the signal. So we're extracting, is it monotonically increasing? Does it have a period, right? Does it look like the classic camel pattern of internet traffic, where it's got like 2 bumps in the day and it goes low on weekends? So we're extracting all of these features from that, and then we just use statistics. So we use Bayesian modeling for that. So we have a set of users that classify these, hundreds of signals into these buckets. We extract characteristics out of those signals and we jam it into a Bayesian or maximum entropy system, and then we say, in a brand new signal, if I take these characteristics out of the signal, I don't know what the signal is, I'm going to take these characteristics out, I'm going to plug it into my Bayesian model. Given all the other stuff I've learned from these users, it's most likely going to be a counter or a force positive derivative. So we use that, right? So as mathematicians say, we're like, is that machine learning? Because the marketing people are always like, is that machine learning, or is that statistics, or is that some sort of like Bayesian classification? And the answer is yes, that's math, right? Because it's all just math, right? So what they're doing there is building probability model around classification. So that is actually really not very difficult at all. You pick 4 or 5 characteristics out of a signal. You build your user model out of it. You put it into a Bayes engine. You can download like a little Python one. You can use R, SciPy, whatever. And now you have a classifier. So that's the first problem. Once we have a classifier, now we can apply the appropriate gauge or derivative or counter or second derivative, all those things, to our signal so that we actually have something that we want to detect anomalies on. So now we have another problem, which is actually a really deep and difficult problem to solve, is that our signals are really noisy. So this same API request per second signal looks fine, whatever. So I'm going to actually look at the last 4 weeks there, and I think that's a whole year, and it looks like this. All right. So it would have been really useful if someone had told me when it dropped there, right? I didn't set a threshold on it. So the whole point here is that when I go and look at a signal like API request per second, I don't want some operator to go in and say, page me or send me an email when it goes above 14, because that requires so much domain knowledge and it's so temporal. Like next week it may not be 14. These static thresholds don't really make much sense. So the holy grail here is, I have this signal of API request per second. It's important to me. Tell me when it's wrong. And I'd like the system to intuit when it's wrong, which is a pretty hard problem. So the question is that the problem you all were looking at? There's actually a huge spike right at the end there, which is interesting, because in truth, that isn't the problem you were looking at. Because if you look at this closely, you'll actually see a whole bunch of really short spikes down as well, because the signal's noisy. Right? It's not a really smooth signal. So this is where all the lies come in. How many people look at 4-week graph like this on a regular basis? You're looking at graphs, right? So each of these points in this graph these are API requests per second. So presumably every single second I actually have a different number of API requests that I've served in that last second. I'm not showing you 86,400 times 28 pixels. So I'm not showing you every single second that's there. In fact, each one of those things is like a 20 or 30 minute average, which is horrible. Because if you zoom in, That's the actual signal. And it turns out that when you see data bouncing around like that, it's actually really difficult to detect a failure in real time. Because what somebody wants when you show them a signal like this is when that thing drops down, they want to be told in like 1 minute. They're like, it broke, you should tell me in 1 minute. It's like, this is happening minute to minute. It's really difficult to tell. And the reason it's difficult to tell is because our sampling frequency is so low. We're getting data so infrequently every minute. This is per second sort of data, but we're getting it every minute or every 30 seconds, which means we need a large set of samples before we can actually be confident, which I'll get to in a second. So if you look back at the original graph and you actually draw just one standard deviation around this, you can see kind of the shit show that exists, right? That there is just huge variability in this signal. So a lot of times in control system, what you'll do is you'll say, you know, this signal's coming in, you should alert me when I go 3 standard deviations away from the norm. So, and I'll get to why that is a horrible, horrible idea in computing systems in general. So there are some simple truths here. I love this one. So 95% confidence linking jelly beans to acne, which is great. People have both, turns out. So in statistics, one of the most important concepts is the confidence in your prediction, right? So if I have a model with data and I have new data points that are coming in and I'm trying to match into a model, I need to understand how confident I am in that. This is effectively a p-value. So if you ever get a p-value, p-values are, so when you're doing statistics and you have a model and you're trying to predict whether something matches your model or doesn't, the classic way to do that, that's called a null hypothesis. So what you're trying to do is not detect how well your model matches your data, this new data point. It's how different does your model match this new data point than no model at all, right? The null hypothesis, like that your model didn't influence the data. And that's a slightly different statistical question. And then when you get the answer to that, you'll get a p-value out of it. And there are a lot of statistical reports where the p-value is like, 0.3, which means nothing. It means that you're absolutely not sure about the answer. And people don't ask these questions often enough. So one of my funny favorite line of a movie, it's from Ron Burgundy. It's like 60% of the time it works every time. What does that actually mean? I dare anyone to come up with a rational explanation of what that actually means. And yet when people are applying statistics to something and they get an answer back, they're just like, this is the answer. It's like, that's pretty much by definition not what probability is, right? So you really need to doubt the data that you're getting, right? You have to have a statistical model and you have to have some sort of confidence factor in that statistical model. And the one thing that can give you much more confidence in a model being correct quickly is higher frequency data. So we have a significant frequency problem. So if I'm sampling disk usage, right, and every time I sample it, it's 80%, and then I get a value that's not 80%, I have a very strong model that dictates that it's 80%. The fact that it's not 80% is significantly different from the null hypothesis, so it's really, really strong indication that it's broken. However, very few of the metrics that we gather are that smooth or consistent, right? You're looking at things like packets per second out of a switch port. And when you derive that, you're bouncing around. You have a very, very noisy signal around like a strong curve, especially if you're a large site. So you have these really, really infrequent samples to build your model, which means that when you get your next sample that says you're screwed, it's only one sample, and you kind of need another one to build more confidence that your new trend is outside of your model, which means you have to wait another 30 seconds or another minute or another 5 minutes, and then how many people here are really like looking to figure out when things are broken 15 minutes late? So we have kind of an expectation crisis here, where people want to collect data, but they're collecting it every minute, and they want to know, like, after 2 seconds that something's broken, which is a fundamental problem, right? You can't do that. Turns out that you can't really detect it after a minute or 2 or 3. You really need some significant collection of that data afterwards to see that you have a change in behavior, right? One data point is not a behavior. So you need to look at that. So we kind of have two options there. One of them is that you just sample faster, or you get more data. And then the other is that you relax your expectations, right? If I have this past thing here, if I go back, this guy, right? No one actually noticed that happened. It actually wasn't a significant problem, but no one noticed that. And honestly, it would have been great if somebody told me after a half an hour, because somebody noticed this after like a week. And it had already recovered at that point, right? So it turns out that the expectation that it would alert immediately, while everybody sort of wanted it, people really would have appreciated it a 30-minute alert on that. So what happens? We kind of have a fundamental problem in small systems because small systems don't tend to generate a lot of data, right? If you have 10,000 machines and you're sampling once every minute, that's 10,000 samples a minute for that sort of data. So now you can sort of synthesize high-frequency data out of that. But I will tell you that I think we can do a lot better with high-frequency data. It's just that we have interesting analytics problems with it. So how do you detect change in signals? Like going back to that drop. What we're actually doing is trying to detect a change in mean. So the mean of the signal over time, some sort of mean, like a sliding window mean or an exponential weighted average or something like that. We're trying to detect when our new signal has a significantly different mean than the old one, right? I'm doing a lot of requests per second, and now I'm doing not so many. Or I'm doing 50 requests per second, and I normally do about that much, and I'm doing 150 all of a sudden. And the mean actually jumps up. So the problem is that there are a lot of different ways to calculate means, and this is where user expectations kind of come into it. So if you have a complex algorithm to detect change, signal change, right, so the model needs to adapt. So if I'm looking at a signal and it drops down by 20%, I'd like to know that. But if it stays down at 20% down for a long period of time, that actually has to establish itself as the new norm, right? So this signal, this mean that I'm comparing against needs to adapt and change. So there's a lot of techniques for this. The two of them that are most common are sliding window means and exponential weighted means. So exponential weighted means are almost always used in control systems. And the reason is because they're incredibly cheap to compute and they have low memory overhead, right? So all I have to do to take, so everybody knows what a mean is, where you add up all the numbers and divide by the number of numbers, right? The average. Okay, so the problem with doing a sliding window, so if you have a sliding window, let's say I have a day's worth of data and I've collected minute samples. So I have 1,440 samples. When I slide the window forward 1 minute, I have to add the new value in that I just received, and I have to remove the old value, the oldest one, which sounds computationally pretty easy, except that I have to store 1,440 values in memory to be able to drop the old one, right? Otherwise, I have to recalculate. Right, so I can do a very simple calculation by adding a new one in and removing an old one out, but I have to know the old value to remove out. I have to remember it. And when you think about 1 minute collection data, that seems not so intimidating. When you think about, say, 10,000 samples a second all day long, now you're talking about 84 million or 840 million or 8 billion or whatever it is. Math, arithmetic. I do math, not arithmetic. So that's a lot of data. So the reason you can't do sliding windows is because the memory complexity is just too high. So I have really high frequency data coming in on one metric. Well, I also have a million other metrics coming in. So I can't keep all of that in one space. So exponential weighted averages work great. Basically, I take my current average and I multiply it by some number between 0 and 1. And then I take the new value and multiply it by the 1 minus that number, and I average them together. It's really easy. So basically, the new number, is 20% or 80% of the average. So the old one, I just say it's 80% of the old one plus 20% of the new one. And then I get a new number in, and I just repeat that and repeat that. And what that does is it smooths the old data into the new data, right? And you can tune that alpha characteristic for how much of a tail of data you really want. This is great. Super cheap. Only have to keep 2 numbers in memory at any given time. It's super fast. It's just multiplication, which apparently I'm not good at, but computers are. So the horrific problem with this is that if you're using this for alerting people when things fail, and then they want to go to apply it to a new signal, and they say, could you tell me when it would have failed over the last week? I want to make sure this is right. How do you go back to historic data and calculate an exponentially weighted window? Right, where do you start? You start at 1970 because I didn't collect data before then? Like, that's really, really expensive to go in and do that. So we have this fundamental problem that the EWM is super efficient and it's really useful in control systems. So most industrial control systems actually use EWM for online control systems. But the fact that we can't repeat that for users to draw them a picture of what would have alerted in the past means that I just lie to people all the time. Turns out users really don't like that. So we need to come up with some sort of hybrid because we can't do them. So in our system, this is just a repeat of what I said. So in our system, what our solution to that is somewhat clever and somewhat gruesome, is that we use this concept of lurching windows, which is a combination of sliding windows and exponentially weighted windows. So what we do is we calculate a exponentially weighted window that's limited at 1 day, and then we keep 3 days of data as one number each, because once you've finished a day out, I can't get any more data in there. So I have an exponentially weighted average for today, from epoch, from midnight forward, and when that day closes out, I just take that average, and that's yesterday's average, and then I have today, which is growing, and then yesterday's and the day before, and then when I go to the next day, I kind of just throw away the last day. So I have these 3-day windows that go in chunks. And what that means is that I have super cheap calculation in the current day, because it's an EWM, right? It's 2 numbers in memory, and I have 1 number in memory for yesterday and 1 number of memory for the day before. And it turns out that that actually works really, really well. So when we put that all together, we still have to do statistics and math. So I'm not going to dive deeply into statistics and math. This isn't the Wikipedia entry for this, but it should look probably very close to it, because you can only do a hypothesis test correctly. You can't do it incorrectly and call it a hypothesis test. So this is a hypothesis test. Basically what you're doing is predicting the probability that your new data fits in the model versus fits in no model, fits in the null hypothesis, like that there wasn't one. Applying this more directly, there is a method called QSUM, which you can look up. It's actually very easy to implement. It's also, there's a definition of it on Wikipedia that any data scientist could probably whip together in SciPy. And what QSUM is it's basically taking your stream data and it's applying a hypothesis model around the means. So the only change that we do here is we use our little lurching window thing to calculate means. And what that gives us is a probability of being screwed up. And this is what the probability of being screwed up looks like. So pretty effective. We know nothing about this signal before this happened. We apply the algorithm and it says, I'm pretty more and more confident that you're screwed right now, and then it resets because we flip back into a mode. So this is exciting. This is really cool. It's nice. Obviously, you only want to do this to signals that you actually care about. So you do this thing around like API requests per second, something that's like a key performance indicator for your service that basically if your CEO would call you and be like, why the hell is blah, blah, blah broken? You probably want to do that to blah, blah, blah. Right? Those things line up pretty well. So we still have a fundamental problem with this in that, so API requests per second is actually a pretty good observation. But it turns out, if anybody's ever been to a velocity conference, the one thing that they have coined there, which I totally agree with, is slow is the new down, right? So if I'm doing the correct number of API requests, but every single user is dissatisfied with my service because they're all taking 2 seconds, I actually have a significant problem. And measuring latency is much more difficult than measuring requests per second. Requests per second, you just count requests and you derive. Latencies, you actually have to track each one of them. So in the past, so before I get into that, so one of the things that's kind of interesting about QSUM and kind of the statistical approach assumes certain distributions around your data. So it assumes that you have a normal distribution of data. We've also looked at two-key, and the two-key test is also, you can find a definition on Wikipedia or Wolfram Alpha, and it's using a student T distribution. The big difference between that is that it's non-parametric, so it's comparing all possible means instead of just piecewise means. So there's some interesting things there. We're looking in that direction and seeing positive results, but don't have anything yet. But the problem is that a lot of the data that we have simply isn't normally distributed. Right? So like all of the statistics that you're trying to apply doesn't apply. Like it doesn't work. Like that doesn't mean what you think it means. Right? So when you're saying, let me take the average and the standard deviation and tell me when I'm one standard deviation away from the average, it's like, who the fuck cares, right? You don't have a normally distributed data. That doesn't mean anything. Like it's an irrelevant statistic, and because of that, you're going to get told things are broken all the time when they're not, and you're going to be told things are fine when they're not, right? So you're going to have a huge problem because the statistical model you're applying doesn't actually meet your data model. This is incredibly obvious in the past thing here. There's two places in this graph where one standard deviation below the average has us serving negative requests per second, which you can think about over beers, right? That's difficult to do in space-time as we know it. So what would happen if we actually had all of the data for these things, like latencies? What if we had full distribution models for everything? So this is a CDN where I actually see the latency for first byte of delivery for every single request being served over all of time. Those are not normal distributions. In fact, you can see some pretty elegant three-modal gamma curves, right? So the second two are really clear. There's a bump, and then there's another bump, and there's a little tiny bump on that, right? Those are your broadband users, your mobile users, and your third world users, or something like that. So you have three different populations of data there. So if you try to calculate something based on standard deviation on that, the statistics don't apply. I mean, you can do it, but it doesn't actually mean anything. So the real problem here is that mathematicians can deal with this. The problem is most data systems can't deal with this. So what happens when you actually get what you ask for, right? So one of the things that we started doing, which is really fascinating to me, maybe we'll write a paper on this soon, if I can get somebody to write, is we've been tracking the microseconds of I/O op latency on every spindle in every box in our data center. Every single IOP against every single spindle. So this is one machine, and you can see where the little gray line is, there's a histogram of data for that. And it's telling me how many of them took how many microseconds. I can see there's a huge spike in the beginning. That's probably around the 2 to 3 microsecond range, right? You can see that is, let's see it here. So the first line is 1K. So that's 1 millisecond. So these are a little faster. These must be SSDs. But so basically what I'm seeing is a distribution of that. This one histogram at that one point in time has 22 million samples in it. So there's 22 million data points that are comprising just that one little vertical thing. And if I move the mouse to the right, I'll see 24 million other samples or 18 million other samples that show me the complete distribution of every single one of these. And this is just off of one machine, right? So now you can imagine that a half rack of equipment with SSDs in it could legitimately generate 1 billion data points every hour. So how do you do math on that now? So that's a really interesting thing. And from my perspective on really being able to detect anomalies, where we need to go that's where we need to go. We need the real data. We need it at the frequency it is. We need to be able to understand the models that we have, because now we have a very clear picture of the workload that's going on with this system, at least the observed workload. And that's the thing that we've found, is that when we measure this workload, and I'll get into, I'll wait a second before I talk about that. But the question is how do you do this, right? So now we have 10 billion to a trillion measurements per second coming into a system. So you need a different model for that, right? I don't even have a system that can pass a trillion messages a second, right? I have my systems and the little message queues that we have. We have 5 minutes? All right. What we do is we end up compressing that. So we use some information compression techniques that are lossy. So we'll take all of the span of data over a minute, and we'll fudge it into a 1 minute time frame. So I'll lose all sub-minute granularity on that data. So if I'm tracking IOPS, the latency on IOPS, I don't know when in the minute it happened, which means that I've just lost a tremendous amount of information, which allows me to compress that signal down very well. And I also add up to about 2.5% of error into the value, and now I can fudge it down. And what that really means is we're actually creating all of that data as compressed histograms. So we're not shipping around values of latencies. We're actually shipping around compressed histograms of all of this data. And the beauty of that is that when you start taking you can apply your statistical tests to characteristics of that data. So here's an example of a characteristic. There's a blog entry by Brendan Gregg called Frequency Trails and Modes, where he talks about trying to determine the number of modes in a signal. Like I said before, there was a gamma curve with 3 bumps on it. I'd like to know that there were 3 different modes in that data. So this doesn't actually work very well. Incredibly valuable anyway, right? So it tends to pull out some interesting data, but what we're doing is we're detecting the modality here. How many different modes of data do I have in my histogram? Well, it turns out that I don't have distribution on that data. So the fact that my original data was not normally distributed means that I can't apply a whole bunch of statistical models to it well, but when I extract the modality of it, that modality stream suddenly applies just fine. I can apply statistical models to that modality. So I can see these spikes are actually changes in workload. Like something's changed. I'm using the disks differently, or the disks are malfunctioning. And what we found is that in our system, if we know that the database, this is a database system, if the database workload is consistent, and it hasn't changed, and one of the disks has a perceived change in workload, I'm about to have a drive failure. And we can lead the smart drive failure status by about 18 hours. So we can see it spike, someone could get paged, they can go to the data center, and about 18 hours later, the smart status will kick off and say, you're fucked, you should replace your drive, right? But they are already ahead of it. They just pop the drive and put a new one in. Before it goes, drives are the worst thing ever, right? Because they're like, you send a request to it, and it's like, I'm going to do that. And like 2 minutes later, you get your data back, and you're like, what the hell happened? It's like, nothing, man, I got your data, right? So they have some really bad failure scenarios. So it's really good to be able to get ahead of them. And if you're measuring the latency on every IOP, you can start to see where all of your outliers come. You can see interesting changes in the workload characteristics. The other thing is you can do arbitrary quantiles. So one of the things that people always say is that I should know my median, my 99th percent quantile. And they're like, no, you should do your 99.9 or your 99.5. And it's like, this is a really interesting argument. How many numbers are we going to go through? If you have a histogram, you can estimate any quantile after the fact. You know your min, you know your max. You can do a 99.5% quantile. Everything's great. So you can calculate all of these things. This one is 25, 50, and 75. I don't know if you can see the bottom one, but you can actually see that the 25 and 50 actually drop in certain places where the 75 spikes, which means that every time someone screws you, someone else benefits. It's like the story of life, just in a disk drive. And then another idea, so this is also the method for calculating estimated quantiles out of histogram data. There's a really great blog post by MetaMarkets that describes the mathematical technique to use there. It's super not complicated. It's linear interpolation, but it's a great article anyway. And then a flip side of that, instead of thinking about like what's my 99.9% latency, usually you have two pieces to a quality of service argument, right? You say my 99.5% quantile is going to be faster than 5 milliseconds. And everybody starts to measure the 99.5% quantile instead of measuring the 5 milliseconds. So you should be doing both. Both of those are nonlinear systems. It's really hard to say, my 99.5 is 2 milliseconds. Well, it could be that you're going to drop off the cliff on the next request. You just don't know. So on the flip side of that, you can actually put in, say, 5 milliseconds, and you can say, what quantile is this? How much % of my traffic is actually faster than my current service guarantee? Which is a really, really fantastic thing to do. So that's it. I think we're about out of time. And there are people smarter than me that work on this. I just try to communicate it really well. So those are two of our mathematicians that think hard. Does anybody have any questions? That's it. Yeah. There's Mike.
There we go. I was just going to ask if you had suggested tools, software packages, et cetera, for doing some of this math on data.
So suggested tools. Our mathematicians use, so I'm super biased, I use the big circle tool because we do all of this in our product. But when our mathematicians are evaluating their techniques, they're using primarily SciPy, even though I prefer R. So I use R and they use SciPy. All you need to do is, you just need a log file with all your latencies, and you need SciPy to be able to do most of this stuff. So like doing a QSUM test and a hypothesis test, all that's fairly straightforward to do in SciPy.
So about histograms. It sounds like a great technique, but I mean, it's actually really complicated because if you, depending on which kind of buckets you introduce, you can easily skip, like, I mean, I don't know, it's like usually my data is like 10 milliseconds for one server and for another it's something else. And then the question is how many of the buckets I need and how fine-grained they should be. And depending on that, you can like easily mess up your whole monitoring. So how do you deal with this?
So I gave a talk on this online in depth. I'm trying to think about it when. It was like 2 months ago, and I can't remember the conference. But very briefly, speak too much. So very briefly, what we do is we generalize the buckets, and we store 2 digits of precision base 10. All of our buckets are spans of 2 digits of precision. So if you think 10 to 11, 11 to 12, 98 to 99, 100, 99 to 100, 100 to 110, right? So you have 2 digits of precision on that. It gives an adequate granularity, right? So you get perfect accuracy with slightly bad precision. So you introduce error into that signal, right? So you're chopping off anything outside of 2 significant digits base 10. And then we can represent buckets. I think in our system we store about 48,000 buckets per histogram. But in reality, when you measure something, the space is usually highly dense. So you'll end up having maybe 400 buckets in a really heavy histogram where you have a data spread. So for example, if I'm measuring something like disk I/O latency, like I'm never going to have a disk I/O latency below, say, 10 micros. And I'm probably not going to have one above 300,000 milliseconds. So, and if it's memory usage, so memory usage in a histogram would be kind of strange because that's more of a value you would derive. I don't know why you would bucket those. But if you do have something offset from 0, so for example, the place this doesn't work very well is if you're measuring the temperature in a very carefully temperature controlled room. So you're at 30 degrees and you want to know when you go to 30.1 or 30.2 because you've lost your precision there. So the answer to that is cheating, is that I know the temperature control is supposed to be 30, so I subtract 30 from my signal, and I actually measure the variation off of 30. But as long as you confine it to that, in practice it's worked very well for almost everything we've done in computing so far. We cheat, but it turns out we very rarely have to cheat. So.
Where would we go if we wanted to learn more about the techniques you've talked about? Are there any textbooks that cover this, other than general statistics?
General statistics. There are a whole bunch of academic, like statistics and probability textbooks. There is a predictive modeling book that I'll tweet out later. It covers probably about 20% of the book is around time series sort of techniques, and the other 80% is around classification techniques, which I think is a pretty good survey of the whole world. But quite honestly, like for the specific statistical methods, it's worth finding the individual method and reading the original paper, and then like doing like Wikipedia search on it. So QSUM and Tukey. So Tukey was a mathematician. The Tukey test. There's a whole bunch of papers that discuss that exactly. But at some point, doing the math is really easy, relatively speaking. Deciding that it was a good idea to do the math in the first place, that's actually a really hard problem. So like if somebody tells me to apply a QSUM signal to it, that's easy. I can just go read Wikipedia and write some Python or whatever. We do Lua. So we write some Lua and I got a QSUM. The question is, should I have done that? Right? It's the same problem that we have today when people are saying, oh, you can just check to see if it's 2 standard deviations away from the average. It's like, yeah, that's actually really easy to do. Should you have done that? And so far, my only answer to that is consult a statistician. All right. Thank you.